Hi everyone, this is Babaiah, Assistant Professor of ECE Department, MLR IT, Hyderabad. Today I am going to explain about the second order system of control system. What are the basic first order systems we learned from the previous sessions when we are going to apply the any input signal to the given first order system, and also from that system's respected output we are drawn in the graph. All these are learned from the previous session, right? Today we are going to learn the second order system. Coming to move on to the here overview of second order system, just the same second order system transfer function. Now we are going to do the here and second order system of the transfer function, and also what is the meaning of damping ratio and how can we representing on the damping ratio in control system here, and also classification of systems based on the damping ratio, and also finally the roots of the roots of the system, that is the characteristic equation from the we are going to calculate the roots. So all these are we are going to learn from the today's session, right? Coming to the first one here, I am going to consider here one second order control system. Here in figure, second order control system, that is this is a figure of second order control system. Second order control system with unity feedback, just before that consider second order closed loop control system, with unity feedback. With unity feedback system, or else with unity feedback. Here this is the second order control system with unity feedback. Unity means here the feedback gain h of s is equals to 1. Here we are going to consider this h of s equals to 1. R of s is, we know, the input, and c of s is the output signal, and omega n square by s square plus 2 zeta omega n s. This is the second order system. Here order is nothing but what previously we learned from the previous sessions. Order is nothing but what the maximum power of the S domain is nothing but the order of that equation, right? Here S domain, in S domain, in denominator part, the maximum power in polynomial equation, the denominator polynomial equation, or else in denominator equation of the closed loop control system, the maximum power of the S domain is nothing but the order of the respected system. Here S square is nothing but here second order, right? This is the second order system with a unity feedback control system. Now we are going to calculate the transfer function. First step here, calculate the transfer function. That is, transfer function is nothing but here C of S divided by output signal to the input signal. Here just the G of S is our in open loop gain. This one is the G of S, consider as this one G of S. Here H of S is equals to 1, and here G of S divided by 1 plus here negative feedback. So here 1 plus with the unity negative feedback, we are going to consider the with the unity negative feedback, right? Unity negative feedback control system. See, okay, G of S divided by 1 plus G of S into H of S. From this, just see, now I am going to substitute in place of G of S, that is the value is omega n square divided by S square plus 2 zeta omega n into S gs divided by 1 plus omega n square divided by S square plus 2 zeta omega n into S, and here H of S is nothing but 1, right? Here omega n square divided by this term, and here by solving this we are going to get here omega n square divided by s square plus 2 zeta omega n into s divided by s square plus 2 zeta omega n into s plus omega n square divided by s square plus 2 zeta omega n into s, right? Here denominator term, this term and here denominator term, these two are same, going to cancel. We will get the transfer function c of s divided by r of s is equals to omega n square divided by s square plus 2 zeta omega n into s plus omega n square omega n square. This is our second order transfer function, second order system transfer function. Also we call it as this transfer function equation. I am going to consider one, and it is the standard transfer function of second order closed loop control system. This is the transfer function, or this is the standard form of standard form of closed loop transfer function. Standard form of second order closed loop transfer function. Here transfer function, right? See one thing here. Now we are going to, this is the transfer function. See here, our first second order system transfer function completed. Coming to the damping ratio, right? Here see, in this equation, from the equation 1, now I am going to write here transfer function, that is c of s divided by r of s is equals to omega n square divided by s square plus 2 zeta into omega n s plus omega n square. This is the equation from the equation 1. Here this is equation 1. From this, just here observe, where zeta equals to actual damping divided by critical damping. Actual damping divided by critical damping, that is zeta is nothing but here zeta is the damping ratio. Zeta is damping ratio. Okay, define this damping ratio. The ratio of, or else damping ratio defined as the ratio of damping ratio defined as the ratio of actual damping to the critical damp. Critical damping is known as damping ratio, right? Here the second point is completed. Next here, now we are going to calculate the next term. Here see, observe, classification of systems based on damping ratio. Here see, transfer function finished and damping ratio also completed, and here see where omega n equals to undamped natural frequency undamped natural frequency radians per seconds units. This is the undamped natural frequency oscillations. Also write here oscillations. Undamped natural frequency oscillation. Simply okay. Radians per seconds, where zeta equals to damping ratio and omega n is nothing but the undamped natural frequency oscillations. Units are radians per second, right? Next, coming to consider the characteristic equation here. Now I am going to characteristic equation is nothing but in closed loop control system, the denominator polynomial is equating to 0. You will get that the equation is known as the characteristic equation. Here transfer function, in this transfer function, in closed loop transfer function, the denominator part is what? S square plus 2 zeta omega n plus omega n square. This equation is equating to 0. You will get the characteristic equation, right? From the characteristic equation, we are going to calculate the we are going to calculate the roots as well as the classification of this system. The damping ratio, based on the damping ratio, we are going to classify the control system into the 4 categories. Mainly, based on the damping ratio, here, based on damping ratio, and also here, the transfer function is going to be changed based on the damping ratio only. A closed loop control system transfer function value we also vary based on the damping ratio also. Okay, here based on damping ratio, that is zeta, based on the damping ratio, the system or control system classified into 4 cases or 4 categories, right? 4 cases or 4 categories. See, now we are going to see all these 4 cases. Here I am going to consider them 4 cases. For the first case 1, if zeta value equals to 0, then the system is going to be what? Here always what I am saying, the response or the transfer function here. See, the response is here C of S, right? C of S. This C of S value or its response depending on the zeta, already previous I am saying. Output of the control system is depending on the value of damping ratio only. Here transfer function, we have a damping ratio, so transfer function also is vary based on the damping ratio, or output of the control system is vary based on the damping ratio. Based on damping ratio also, the system can be classified into the 4 categories. One is the zeta equals to 0 condition. Here if the zeta equals to 0, the system is going to be undamped system. If zeta equals to or damping ratio is equals to 0, then the system is undamped system. If zeta equals to 1, critical damped, I am going to write here zeta equals to 1, that is critically damped, critically damped system. And next here, if zeta value between case 3, zeta equals to 0, the system is undamped, and critically damped for zeta equals to 1. If zeta value is less than 1, or else between 0 to 1, for example 0 to 1, zeta value between 0 to 1, then the system is under damped, right? 0 to 1, right? So under damped system. Under damped system, last case is if zeta value greater than 1 condition, greater than 1, so then the system is over damped system. Okay, all these are 4 systems. Next, I am going to calculate the roots of the system. For each and every cases, what are the roots are going to be from, or else what are the roots we are going to get when we are going to apply the zeta equals to 0 or zeta equals to 1, zeta between 0 to 1 or zeta greater than 1 condition also. Now I am going to consider the characteristic equation for the calculation of the characteristic equation. Nothing but water in transfer function, the denominator polynomial is the characteristic equation, that is consider for roots of the system. Consider the characteristic equation of second order system, that is s square plus 2 zeta omega n into s plus omega n square equals to 0. See here, this is the second order system characteristic equation. So here characteristic equation which is in the form of quadratic equation, right? So quadratic equation ax square plus bx plus c like equals to 0. Here a equals to what? 1, and b equals to 2 zeta omega n, and c equals to what? Omega n square. C equals to omega n square. Just substitute all these in formula, just ax square plus bx plus c. In quadratic equation, use the formula here minus b plus or minus here s1 comma s2 minus b plus or minus under root b square minus 4ac divided by 2a. Just substitute minus b means here minus 2 zeta omega n plus or minus b square 2 zeta omega n b square, and here minus 4 ac, where a is 1 and c is omega n square, right? It's root, under root this one, divided by 2 a is 1. Okay, now s1 comma s2 roots of the second order system is minus 2 zeta omega n plus or minus here 2 zeta omega n square minus 4 zeta omega n square. See here 2 omega n just common here 2 omega n square, so 4 omega n square, right? This is 4 and zeta square omega n square. Here also 4 omega n square there, so 4 omega n square comes or common from the root. We are going to directly write the minus, directly 2 omega n right? 2 omega n is common. Next here zeta is there, zeta square minus 1, right? 1 root and square both cancel, so here 2 omega n directly I am writing here divided by 2. Here 2, 2, 2 are there. Here 2 common, and just cancel these two. Minus zeta omega n plus or minus here omega n, and also here simply zeta omega n square plus c. Just substitute here omega n square or omega n under root of zeta square minus 1, right? Okay, minus 1. Here s1 comma s2. s1 comma s2 minus zeta omega n. Here 2 both cancel, minus zeta omega n plus minus omega n under root zeta square minus 1, right? Okay, leave it, this one. Next, these two from this. Next again, calculate the roots by using this equation. S1 S2 equals to minus zeta omega n plus or minus omega n under root zeta square minus 1. Under root zeta square minus 1. This you can remember this one. Okay, now we are going to calculate the roots. Next, move on to minus zeta omega n plus or minus omega n. Sorry, minus zeta omega n. See here. Here this is the equation. Just substitute for S1, S2 roots. For the case 1 condition, zeta equals to 0, right? Zeta equals to 0. Substitute zeta equals to 0 in this equation. Equation 2, for example, zeta equals to 0. Substitute, you will get the 0 value. This value here 0 minus 1. So plus or minus omega n. Zeta equals to 0 is nothing but undamped system, right? Undamped system. So plus or minus omega n. Roots are plus or minus. Plus omega n 1, minus omega n another 1. So that means roots are going to be purely real or imaginary? Real only. So purely, sorry, one thing, here zeta square is there, so I am going to here common one root and square. See, zeta square minus 1. I am going to write here zeta value going to be what? Here this one is 0 and here 0. So minus 1 root. So j square equals to minus 1. I am going to write j square. So in place of minus 1, j square, square root get cancelled. So plus or minus here omega n is, that is nothing but j omega n. I am going to write here j is there. One more, here j is there. So j omega n. So directly this one, roots are purely imaginary, right? So because of imaginary part is there, purely imaginary. Okay, next, for example, zeta equals to 1 condition, s1 comma s2 equals to what? Here j square equals to minus 1. I am going to write here j square equals to minus 1. Okay, it is visible, I think you. Okay, zeta equals to 1, s1, s2. Again substitute 1 in place of zeta, 1 minus omega n plus or minus omega n. Here zeta 1, 1 minus 1 is 0 and 0 root, this value is 0. So plus or minus omega n only. Here minus omega n. So minus omega n is s1 equals to minus omega n, s2 equals to minus omega n. So both roots are equal, right? So equal roots, real and equal. Roots are real and equal. Roots are real and equal. Then the system is, this one is undamped system. This is, then the system is critically damped system. Wait, here I think not visible. Roots are real and equal. In zeta equals to 1 condition, we are going to get like real and equal. So the system is System is what? And system is critically damped. Zeta equals to 1 condition and damped. Zeta equals to 1 critical damped. Roots are the real and equal. And zeta equals to 0, roots are purely imaginary. Then the system is the undamped system. Next, last third case here, observe. Zeta equals to, or else zeta between 0 to 1. 0 to 1, that is the case of underdamped, right? Underdamped condition. So underdamped condition, the characteristic equation is from roots equation is minus zeta omega n plus or minus omega n under root zeta square minus 1. But zeta value less than 1, no, greater than 0. Zeta value is in this condition greater than 0 and less than 1. So here S1 comma S2 is what here? Minus zeta omega n plus or minus, and omega n under root zeta square minus 1. Here zeta value is greater than 1. So, but here zeta value is less than 1 condition. So, we are going to just zeta value is less than. We require zeta value is less than. So, here zeta value. So, minus 1 I am going to consider. Here minus 1 common from this equation. So, here minus zeta omega n plus or minus. Minus 1 common means here minus 1. Here minus 1 and 1 minus zeta square or 1 minus zeta square. Minus 1 into 1 minus 1 and minus 1 into plus minus zeta square. Okay, I am going to write like this. Okay, next this equation again going to consider as minus zeta omega n plus or minus, here minus root minus j square equals to minus 1. So j square root get cancelled. So j and 1 minus zeta square root. Okay, see here. Now this equation, zeta value is going to be less than 1 and greater than 0. So that's why here next I am going to write zeta under root 1 minus zeta square. Where is omega n also is there, right? Omega n, and here also into omega n. Okay, so omega n into this value, omega n into under root 1 minus zeta square. I am going to directly write this one, omega n plus or minus j into omega d. In place of omega n, omega d equals to, just I am going to write the 1 omega n 1 minus zeta square. So substitute that directly. Omega d is nothing but the damped frequency oscillations. Damped frequency oscillation, the roots are going to be just here, observe, imaginary as well as real. So imaginary value as well as minus zeta omega n plus j omega d or minus zeta omega n minus j omega d means here these two roots are not equal, right? Not equal. As well, roots are what? Complex conjugate. Both are imaginary as well as real. So that's why directly simply the roots are complex conjugate. Then the system is underdamped system, right? Last finally case for S1 comma case1, zeta is greater than 1 condition. So directly that roots are directly going to be what here? S1 comma S2 equals to same this value, like this equation directly minus zeta omega n plus or minus omega n under root zeta square minus 1. Because of here zeta value is greater than 1 only. So here greater than 1 directly write the minus zeta omega n plus or minus omega n under root 1 minus zeta square under root 1 minus zeta square. This is the roots of the critical damped. So means here critical observed roots are unequal but real and unequal. So roots are real and unequal. Real and unequal. See here, observe. For the underdamped condition, roots are going to be complex conjugate. That is zeta value between 0 to 1. If the zeta equals to 0, that is nothing but undamped condition. The roots are going to be imaginary, means purely imaginary roots we are going to get. When we are going to substitute zeta equals to 0, that the system is the undamped system, and zeta equals to 1 condition, the roots are going to be real and equal. Because of zeta equals to 1, when we are going to substitute in the roots equation, from that equation we are going to got the roots are real as well as the equal, because of s1 equals to minus omega n as well as s2 equals to minus omega n only. For the critical damped system, the roots are going to be real and equal. For the underdamped system, roots are going to be complex conjugate. For the critical damped system, the roots are going to be real but unequal. And for an undamped system, the roots are going to be purely imaginary. All these are the cases, all these are the roots of the system. The systems are going to be classified based on the zeta or 4 types. Zeta equals to 0 condition, and that is undamped, zeta equals to 1. For critical damped, zeta between the 0 to 1. Under damped system, zeta is greater than 1 condition, that is the critical damped, zeta is greater than 1 for over damped system. All these are the 4 cases for based on the damping ratio. The system, second order system, can be classified that. Okay, all these are the roots, and also roots as well as from the characteristic equation, based on the 4 cases, we got the roots from the second order system. I hope you understood everything. Just to move here, see once again, just second order transfer function. What is the second order transfer function? Here, this one is second order transfer function, the equation 1. C of s divided by r of s equals to omega n square by s square plus 2 zeta omega n into s plus omega n square. This is a second order transfer function. Also, it is the standard form of closed loop transfer function. It is very, very important. Standard form of closed loop transfer function this is. And next, damping ratio. Damping ratio in that characteristic in second order closed loop control system or a standard form of closed loop control system, from that zeta is there here. Zeta is nothing but damping ratio. What is meant by damping ratio? The damping ratio is defined as the ratio of actual damping to the critical damping, where omega n is nothing but the natural frequency oscillations or undamped natural frequency oscillations. Radians per seconds are the units, and based on the zeta value, or else C of s, the output is always depending on the damping ratio, or else it can be vary based on the zeta value. Based on the zeta value also, the system can be classified into the 4 categories. What are the 4? Zeta equals to 0, the system is undamped, and zeta equals to 1, critical damped, and zeta between 0 to 1, under damped condition, and zeta is greater than 1 condition, over damped system. For the each and every system, we are going to see the what are the roots here. All are from the characteristic equation. We are going to observe the roots. For the undamped system, zeta equals to 0. For roots are going to be purely imaginary. Okay, and roots are real and equal for the critical damped system, that is zeta equals to 1. For zeta between 0 to 1, the underdamped system, the roots are going to be complex conjugate. If the zeta is greater than 1 condition, overdamped condition, that is the roots are going to be real but unequal, right? All these are the cases and transfer function and basic cases of the based on the damping ratio. The 4 different categories of the systems are available. 4 different second order systems are available in control system. Okay, I hope you understood every point. I think this one is the very second order system is very important. From that we are going to derive the critical damped system, undamped system, underdamped, overdamped. From these four cases are very important for your any technical exams or any competitive exams. Okay, I hope you understood every point. I hope you understand every point, every each end point. I hope you let next class we are going to again meet. Thank you all.